Okay, we can wait a little bit more before starting.
Do we want to record the session, Maria?
Yes, it's already started.
Okay, good.
And we have more and more attendees, so I think we can start and the others can join later. So good morning, everyone, and welcome to the 11th ETP4HPC webinar. Today, Zoltán Horváth, the president of EU Masin, will show you a TCI use case on urban air pollution. Üdvözlöm, Zoltán, welcome. I am Maria from ETP4HPC office. I will be the host of this session, and two of my colleagues, Pascal and Michael, will help us today. Before we start, here are some useful information. This webinar is recorded. You will receive the link to the recording on Monday. The webinar is in listen-only mode. This means that you can communicate with us. You can ask questions via the question pane that is illustrated here, you can see, and this is on the right-hand side of your own computer desktop. Here you can also find the handouts. Today we have 3 files there, the slides of the presentations, and also 2 of our recent publications. One is the European HPC project handbook. This is with almost 70 ongoing projects related to HPC. And the other one is a white paper on processing in memory. And today's main focus will be the urban air pollution use case of TCI, presented by Zoltán Horváth. Before that, my colleague Michael Mums will present you quickly what is TCI, what is the Continuum initiative. We will close with a Q&A session where we will answer your questions, and the plan is to finish at 12 today. And a couple of words to present you Zoltán. Zoltán Horváth is a professor, is the head of Department of Mathematics and Computational Science. He is the president of EU Masin and also the European Service Network of Industry and Innovation. And at the same time, also the strategic research agenda coordinator of EU Masin. Besides this, he is also the coordinator of several EU-funded projects. And his focus of research are simulation of acoustics of exhaust system of cars, digital twins for urban air pollution, and applications of machine learning in healthcare. Thank you for being with us today, Zoltán.
Thank you, Maria, for the introduction.
And Michael, now I give you the floor to present us the Continuum initiative, please.
Thank you, Maria. So 2 minutes on TCI. This is a kind of an elevator pitch, 2 minutes. So in the center, you see many disciplines that are all required and important. I don't see the charts anymore, Maria.
Do you see it now?
Okay. Thank you. So in the center, you see the wheel with all these domains and disciplines that are required to implement the so-called digital continuum. And TCI initiative means that associations that are representing these domains have decided almost a year ago, to collaborate on identifying R&I priorities for future work programs within this continuum. And on the next chart, we then see that we started to work on use cases. So analyzing use case together within the set of these 8 associations is up to today the most important element of TCI. You see 3 use cases, all in the area of digital twins, and Zoltán is talking to one of them, the latest one. There are previously handled and mentioned use cases in the real-time digital twin area in the industry, and also in the area of environmental protection, the extremes prediction use case. You'll find the white papers on those letter 2 ones already on the web page, the ETP web page, on the so-called Zenodo platform, and you will see very soon also Zoltán's use case show up there. But today Thank you, Zoltan, for showing us the latest developments in this use case. And with this, I hand over to you, Zoltan.
Thank you very much, Michael. And also, I'm very grateful to ETP4HPC for inviting me for this task to coordinate the urban air pollution. I don't know whether you can see my screen.
Yes, we can.
Yes, we can.
Excellent. So this is a TCI, the Transcontinuum Initiative's use case, the urban air pollution, which is a platform for collaboration between the participating 8 organizations. And our aim is that we together can propose the European Commission and the bodies of the European Commission good challenges such that they will translate it to project costs. And I strongly believe that together with these platforms, HPC, big data, IoT, cybersecurity, mathematics, and other platforms, we can do a much better job, which is now the state of the art. So we can help people for a better air. So the contents from sections 2 to 5, these are the sections of the white paper. As Michael said, we are writing a white paper, and we would like to, together with the TCI members, and we are using this white paper as a communication material with other bodies, EC bodies, for getting some calls with these priorities. So for the purpose of TCI was already summarized by Michael, and now a white paper is under drafting, and this presentation follows the current draft, and further contributions are welcome from each TCI member. So probably some of the TCI expert, some people from the TCI expert groups are present at the meeting, but if not, please feel to contact me as coordinator of this white paper to add some materials there. So the first topic in the white paper of the TCIs is the relevance and why is it relevant to the transcontinuum. So the relevance of the material for societal purposes is clear. 3 million people die per year due to high level of air pollution in cities. This is proved by several reports, some of them by WHO. 3 million per year is a very huge number, proportional or nearly the same as COVID does, or something like that. And this is for many decades going on. So currently predictions at core scale exist at EU. So I will show you some what is presently given, and from the Copernicus services. But cities need higher resolution and fast solutions for monitoring, prediction, and control to diminish the harmful effects of the air pollution. So we need high resolution, higher resolution prediction of the air pollution or monitoring. By the way, monitoring with measurements is very expensive, so simulations play a key role. For validated simulations play key role in this subject. So the members of the transcontinuum are, and the contribution is expected from there, and with a harmonized action, we together can provide better solution on this topic. Namely, a fast and detailed measurement is needed of traffic and other emitters. So 5G, smart sensors, networks, IoT contributions expected on this topic. Recently, only occasional measurements exist in cities, from one city to the other one different. So somehow unified solution that can be deployed to any European cities would be very much in favor of politicians and people. If we have already measurements from the urban air pollution, then we need high resolution and fast simulation and analytics of the big amount of data that we produce from simulations. Clearly, HPC, cloud, edge platforms, mathematics algorithms, and HPDA AI play a key role in this topic. And when we have the simulation results and analytics from the data measured by some smart system, smart sensors, we would like to provide a control mechanism to complete the circle in the sense that not only predict and monitor air pollution, but also act to diminish the concentration rates. And clearly, for this operational control system, which runs automatically, this would be a cyber physical system. And of course, cyber security plays a important role here, and some other contributions from smart networks, AI, meta algorithms are important in this topic. So from these 3 bullet points, we can see that indeed the whole transcontinuum is attached to here. The second point, what are the key insights of this pilot? Accurate and real-time sensing of emitters is very important, which doesn't exist now at affordable price. Each city has only 1, 2, maybe 5 containers that measure in a certified way the air pollution. So an accurate and real-time sensing is important, and not only directly the emitted pollutants, but also the emitters, that is the traffic, household, industry, and agriculture is important. Maybe we can focus for now on traffic, which is one of the main emitter for many pollutants, and clearly for nitrogen dioxides and other harmful gases, this is the key emitter. So we would like to sense traffic. Faster than real-time simulation of the urban weather, urban geometry, 3-dimensional geometry is very complex, and running simulations on these complex domains is very difficult. And this is one of the key aspects of our work, to provide faster than real-time simulations for the urban weather, how the wind goes on streets, and the air pollution dispersion on that wind field. And for that, clearly, we have to couple data that we measure and also which are coming from other big instruments like Copernicus services. We have to couple these data to our simulations, and this is a very uncertain system. We have to quantify the uncertainty. So when we have good simulation, fast, good simulation, then we need to analyze the data very fast, the big data, and maybe delete what is not necessary, and extract the crucial information for planning and control purposes. Air quality control system that fits smart city solutions is very important here, and standardization of the whole process is extremely important for deployability and usability. So we don't want to develop and propose to the European Commission a solution which is just occasional, but we would like to propose a solution which can be applied to almost all European cities, if not all. So the key recommendations that we could formulate, and which is a consequence of our TCI group meetings, is to develop a measurement methodology of the traffic emissions, which is applicable to many cities, and create bottom-up emission inventories. Hierarchical weather and climate models with urban, regional, and global models in an operational way. Let me mention that regional and global models do exist now, but we have to somehow add the finer scale, 1-2 meter resolution at the street level, validated modeling and simulation urban wind, and dispersion of the pollutants, reduction of complexity of computation to get fast simulations, faster than real-time simulations. If you would like to use it for control, we need very fast simulations. So real-time digital twins actually have to be developed for the urban air pollution. And smart city solutions are needed for the control and standardization of the process. So let's go to the details of the use case. We agreed at the beginning of this TCI procedure how to have an impact on the European bodies to propose research recommendations, to propose some research topics, is that to investigate use cases in details which do exist and generate challenges. And one of them is this urban air pollution. And now let me investigate one use case for existing solution, which is not fully complete. That what are our aims clearly, but let me show you this. Here is the link to the WHO report, and clearly EC provides help cities with predictions, but these predictions are only global. If you have a look at the left pictures, you can see what results we can see from the web, that one city, one number, with some dispersion of the predicted NO2 value, for example, for each 3 hours. But from the right, from an HPC simulation, we can see hotspots that appear, that are present in a city for a longer time period. So clearly, what is now provided is not enough. And HPC, if we can define, implement HPC solutions so that city authorities can run them easily, then this would be a good opportunity for the HPC developers to develop a product that is used by everyone, actually. So, but maybe this doesn't exist yet. So, the next topic in the white paper, we are discussing what are the business drivers and the societal impact. Clearly, one of the main business drivers are the cities. Let's focus now on the work programs, the Horizon Europe and the joint undertakings work programs. There are several existing calls that are in the topic of urban air pollution. For example, by the EGBA joint undertaking is initiative, the 2.0 program partnership is one of the chapters that in the present work programs have been maybe open course. The main chapter, which is one of the key topic in the European research and innovation activities, is the climate, are the missions, the climate city mission. I copied from the European website the timeline, and here in the third and the fourth quarter of this year, they are launching the missions in full implementation phase, and they will update the work program with those. So maybe a little bit we are late, but because they are now drafting these missions topics, but we are not late for the next period of the work programs. And there is one dedicated mission for the climate neutral and smart cities in Horizon Europe, and to transform 100 climate neutral cities by 2030. And this has several topics which are clearly in line with with our activities. The stakeholders, maybe this is clear. Who are the stakeholders? And the solution I'd like to provide you our results are developed from the Hidalgo Center of Excellence, now ongoing Horizon 2020 project, and our university's projects. So we would like to provide a microscale simulation as a service in very high microscale simulation for air pollution at very high resolution, which runs on supercomputers and on edge online, faster than real time, and so on. Let me summarize this. I put some appendix slides to the end of this presentation to see some details, and I copied one picture from there just for those who would like to try it, what we have developed. So our urban air pollution pilot is accessible through the net with this demo account. You can see here with a little bit restricted features, and we have training materials for that. You can request, and I'm sending to you if you need. And we have developed already a service with that. We run our simulations for Györ, a city in Hungary of 130,000 inhabitants. We run this reanalysis, and you can run it. You can see the results and evaluate the visualizations. In this meeting, I have just the opportunity to have a quick overview of the technical details of the urban air pollution use case, but probably some of you from the participants have already listened one of these presentations. So this slide is an overview of the workflow. We have data acquisition and provision. There are modules to get traffic data, weather data, and air quality data. Traffic data are coming in our use case for the city of Györ, a very modern system of traffic observation, namely plate number recognition, camera radar units where the cameras are can understand the plate numbers, and we can follow the path. Weather data from the ECMWF, weather forecast simulation from the Polytope API, and the Bosch emission monitoring boxes, 5 boxes on the top of the 2 national containers are available for the project, for the use case. And we have air quality. So from these boxes, we have weather data and air quality data, also concentration of nitrogen dioxide, ozone concentration, pollutant materials concentrations are also coming from here. And from the Copernicus CDS API is also coupled, automatically coupled to our system. We need some pre-processing, of course, the emission measurement and computation. The first building block of the emission box is the traffic simulation, then calculation of the emission from the traffic quantities. Then we have the airflow and dispersion simulation, and I will go to a little bit more into details in the next slide, and post-processing with HPDA and visualization. All of these can be run from the portal of which link I shared with you 3 slides before, and we have this workflow, and the workflow is modeled in a Tosca language, and from this Tosca blueprints in a YAML file are created, and then executed with the Cloudify orchestration and with HPC plugin, Croupier. Actually, we have developed an even better orchestration, which provides more information from the run of the solvers of the jobs during the simulation time. For example, this is the new feature of it. Visualization, we have an interactive visualization tool, and access from the portal. You can see here this simple manner. You can fill in some text files in a nice way, and you can have here a dashboard, and you have a 3D visualization and also gallery information. And you can, all of these features, you can test them from the link. We have open form solution for the full order model, which is pretty much scalable depending on the size of the problem. And we have also a novel AI-based solution for the airflow. Namely, this is the skeleton of our workflow here. And here we have this reduced order modeling box here for the airflow computation. So we can choose between to run a full order model or run an AI-based simulation, which has an offline and an online phase. And so we train in offline our online model, fast online model, with running several times with several configuration parameters, some simulations. We extract information these are running on HPC hardware. Clearly, we need strong HPC or cloud infrastructure here to run several cases for the training. Then we extract information from the training, from the snapshot matrices, and to find the most relevant directions in the state space, which are important in the simulations, and we extract some matrices. And the online simulation reads these matrices, and even on edge platform or a sim CPU, one CPU or two CPUs, this is the most efficient in our case up to now. We run the reduced order simulation model, and which provides the output. This can be seen from this YouTube video. We don't have time for that now to investigate it, but you can run it if you wish. And we get this kind of results. FOM is for the full order model, which runs, for example, CPU 1 core. Just for a test case, maybe it is 200 seconds. And for this test problem, on a CPU 8 cores, you can see the results here. And also here you can see the reduced order model, how much time we need for that. And we can see here a very significant improvement of the computation time when we use this reduced order model, this mathematical technology to make these simulations even faster than on GPU or whatsoever. Let me mention that we have developed multi-core software for fluid simulation, which runs very efficiently on GPU. On one GPU, that software runs 200 times faster than on one node, with 32 modern cores. So this is the implementation. I have already told you this information. So let me go to the next slide and to go to the challenges. So this is a physical model based, physical model because we run actual Navier-Stokes simulations calibrated to weather simulations. But otherwise, it is the very same as the industrial digital twins, and the research priorities are the same. But let me go to the research priorities that we have to fix with our TransContinuum initiative partners. Now, this finalization of the research priorities from partners are ongoing and not fixed yet. So let me go through these research priorities through the modules, according to the modules of our solution. So we integrate, so what are the challenges? One of the challenge is the geometry for the traffic and the airflow simulation and the dispersion simulation. So we need accurate 3D modeling, and now we are using OpenStreetMap for that, but more accurate databases would be very useful if you could integrate to the workflow. This is a challenge, how to make an automated module in the workflow. Then integration of smart sensors and network tools into traffic data acquisition in a unified way. This is extremely important. The weakest point of this urban air pollution modeling is to get emission data. and emission data, and the key point to get emission data is the traffic simulation. And for the traffic simulation, we need traffic data. And there are currently we have many smart sensors and smart network tools that may sense the traffic, vehicular traffic, and but no unified way exists which can be deployable to any cities in Europe. So it is very important to define this kind of ways of traffic sensing. For the traffic, it is very important, again, and it's a challenge, how can we define a purely data-based traffic simulation model? The presently existing, the currently operational commercial software are based on actual physical simulation model of the cars, taking into account driver behavior and something like that. But it's very, very difficult to set up a validated traffic model. And what is a surprise, most of the market-leading software on this field are running only on one core, one CPU core, and these are pretty slow for the control purposes. So it is a very important topic here, whether we can, if we have already good data from the traffic sensing and enough data, then to define AI methods for traffic simulation. The weather data.
For your information, there is 5 minutes left from the presentation.
5 minutes. Okay, thank you very much, Maria. So the hierarchical model setup and integrate urban air pollution models to the existing Copernicus and other systems, that is operational global models. And of course, data simulation and this AI-based path simulation provides a lot of material for mathematical and HPC and AI research to define them. Very important are the standardization aspects and the control aspects. So let me conclude now. We justified the facilitator challenge, stakeholders, related EU work programs, and we have seen in details with the TCI partners one use case. We implemented modules. These modules have to be improved, or similar modules have to be improved and standardized. The next actions that I propose and that we are a little bit delayed what with Michael we planned, but maybe the following roadmap is suitable. So everyone, so I'm sending the draft of the white paper on Monday, next Monday to the TCI partners, and send the doodle for bilateral meetings to fix their contributions. Everyone is welcome, even if they are new on the topic. Bilateral meetings with TCI partners will be till 8th of October. Final draft circulated 11th. Approval by TCI partners and completion white papers will be done till the end of October. I think this is a doable roadmap, and we can and we must do it, not to be too late, not to be late with missions and with other negotiations. So last, let me thank our project partners, the Hidalgo and my university's projects, and the Hungarian UAP-HPC competence centers for supporting this work. And if you received this material, you can see here an appendix with some other details of this use case. Thank you for your attention, and I would be glad to get questions.
Thank you, Zoltan. So this was very interesting. This was a good update on what you had presented in this TCI working group before. Let me go to one question that was posed by Henry Strauss. So let me read the question to you, Zoltan, and then you can answer this, okay? So Henry Strauss is asking, currently an FF4HPC proposal named Holistic Environmental Energy Modeling of Buildings and City Quarters is in the works. Although it is not directly related to your work, I see a lot of potential synergies. What do you think?
I haven't read that UAP proposal yet, but this is clearly very much related. For example, if you want to simulate the building energy consumption, then definitely you need to simulate the wind and the temperature around the building, and therefore a huge part of this urban air pollution pilot overlaps with those what are requested there. So clearly these are very closely related.
So maybe what we could do is, Zoltan, that Henry Strauss takes advantage of this presentation and gets in contact with you.
Thank you.
You have your address here shown on the acknowledgement page. So maybe we can make that connection, and then you can hear more about this work being done. There is another question from Graham Collins. So this high resolution modeling and prediction will be invaluable for predicting the contribution to lung infections, including COVID-19. How would you suggest this simulation data is used most effectively to show the contributory effects for COVID-19 and other respiratory infections?
There are several papers in the best journals, even in the best journals, that makes an evidence that air pollution and the spread of COVID is correlated positively. And so clearly these are, after reading those papers, these are clearly, this is an existing connection. I had no time to focus on that too, but if anyone has an intention to get data from us, we would be very glad to provide detailed air pollution data to those research groups who would like to analyze this correlation. You know, we experience that within cities there are some regions where the air pollution level is much worse than the average of the city, and maybe on that region the COVID spread is higher, as expected from the research papers. But I had no chance to find time for doing my stuff. But for any similar research, we would be glad to provide data and simulation tools.
Okay, thank you. Another question from Michael Meiser from Vicom Tech. What kind of control actions are you thinking about to implement?
We are not only thinking about it, but one is ongoing within the Hidalgo project in Györ. Namely, we are doing the following. This is the simplest what is reasonable. in Györ, there are several main roads where the traffic lamps are harmonized, and we take one block of this harmonized one big street with some connecting lower where the traffic lamp is controlled by devices from the Public Road Ltd, National Public Road Ltd, and we can switch off between the existing programs according to our predictions. And this is now ongoing, and we hope, and it is not hope, but we are working on getting one result by the end of October, or at least at latest in November. So by the end of November, I would be very glad to share information how we could make it. So summarizing this long sentences, simulate possible scenarios and choose the best one according to the air quality and traffic conditions, restrictions, and then change the best program according to that. We have already figured out together with the company, the traffic company, how to change the programs automatically from software. This is very sensitive process, so we don't want to change, we don't want to create new programs yet, but for this validate proof of concept study, we will change only between existing programs.
Okay, all right, good. So I think this is the set of questions. Yeah, let me ask you a question, Zoltan. So when you talked about the required elements and the research priorities, you talked about very fundamental elements that are needed in order to improve the quality of these predictions. Now, thinking out into the future, let's assume you not only have one city that is using this infrastructure, but you have multiple cities. Let's assume, very positively thinking, you have maybe 100 cities using this modeling. Do you see any requirement for further research to make this approach scale?
For doing research, sorry,
yeah.
I didn't the last
each city does this modeling for itself, right? Do you see each city as, let's say, a closed environment, or do you see that there are fundamental workflows and simulation flows across these cities and into the service of these cities then, so that the scalability of this approach is and might become an issue?
I'm not sure that I understood correctly the core, but I think that this not saying, but I'm sure that this method that we propose is self-adaptable to cities. That is, it extracts the most important information from the wind and everything and all other information, and we don't have to know a priori anything, just measuring. What is important that in many cities in Europe there exist almost infinitely many ways how to measure the traffic. So many cities have own method how to measure with this software, in this way, that way. There are many different ways to simulate traffic in the cities, but we have to standardize this process, and then if we make it, this is a research how to make a synthesis of the existing ways for traffic simulation, and then we can apply this HPC AI-based methodology immediately. But we have to convert many ways of traffic information into one general one. This is the first point. And the second one, which would be the most useful for many cities who has no existing simulation tool for traffic, to provide them a methodology and tools how to measure, and with some smart sensors, and they would be very happy. I know several cities who would be very glad if they could buy a standard way to measure the traffic. And then it will be scalable. So this is the drawback for the scalability and the applicability of the use case.
Yeah. Okay. Thank you. So I don't see any other questions.
No other questions coming in.
All right. So do you want to spend some time on the next webinars maybe? Or are we at the end? So I hand over to Maria and to Pascal.
Yes, thank you, Michael. And also thank you, Zoltan, for your presentation. And also thank you for all participants for being with us. I would like to ask you to please fill in the survey once you leave the webinar to help us improve future sessions. You can already see the list of the next webinars, and you can already register for those you are interested in by clicking on the links. You can also find here our contact details. Your suggestions, questions are very welcome. So thank you again for all of you, and I wish you a nice day.
Thank you.
Goodbye. Bye-bye.
Bye-bye.
Bye. See you in October.